The longest common subsequence problem gives us two strings, let's say ABCD and BACD. And it wants us to find the longest common subsequence shared by these two strings. So what's a common subsequence? It's letters in both strings that are in the same order, but not necessarily consecutively. That would be common substring. So for example, we can say that both strings have an A. So A can be in our subsequence. But then as we move forward, we can encounter a B in the first string, but moving forward, we're not going to see that B. We'd have to move backwards to see the B. So B's out. They're not in the same order. We can move forward in both strings though and see the C. So C can be in our subsequence, as can be the D. That's not the only answer we can have. We can start with the B instead of the A. Then as we move forward, we again encounter the C's and the D's. So there's two possible answers. Either way, we're going to return 3 because the question is asking us to return the length of the longest common subsequence. We could do the subsequence itself. What's the longest common subsequence? That's a separate problem, which we could do later. But for now, we're just after the 3. Now that we know what our goal is, let's think about how we would go about trying to solve this problem. Your first solution, don't worry about dynamic programming, just try to solve it. And you want to do that anyway, because when you do have a dynamic programming solution, you're going to want to compare it to the non-dynamic programming solution, just so you can see how cool it is. Anyway, so we're just going to try solving this with recursion. So if we said ACD and BCD, remember, those were the solutions that we got when we just did this manually. And there's a hint here that they're the same solution, just the first letter is what could be different. The constraints of the problem are that the letters have to be in the same order. Then there's no harm in starting from the back of the string. The letter in the back of the string cannot disrupt the order of anything else. The D's kind of come for free. It's like, why wouldn't we include it? Basically, we're going to turn this question into a slightly simpler question, which is, what is the longest common subsequence between ABC and BAC, and then +1, because we can tack on a D at the end. It's going to be the same thing. Solve for ABC, BAC, and whatever solution you get for that, add 1. Now we have the same thing in this problem, though. They both end in C. So the C is the freebie at this point. This is the same thing as asking, what's the longest common subsequence between AB and BA, and then +1 for that free C. And that matches what we saw in our solutions, right? The C and the D were included regardless. So now the B and the A do not match. So here's where we get to ask ourselves a question. Could we include the B? Like, yeah, possibly. The B could be in our subsequence. How about the A? Yes, possibly. But if we include the B, then we cannot have the A. And if we include the A, then we cannot have the B. So this is going to split into two different questions. We'll leave the B in our first string, but then we have to drop the A from our second. Or we can drop the B from our first string and then leave the second string alone. Since we're after the longest common subsequence, we're going to take whichever one gives us a bigger number. In this case, A, B, and B, well, the B's match. So we're going to do what we were doing before. We're going to drop the B's and add 1. So it's going to be A and an empty string +1. And over here, it will be an empty string and B +1. As soon as you have an empty string, you cannot make any subsequences from it. So we know that our answer is going to be 0. So here, this can just be a 0 +1, we return a 1. And here, this is also a 0 because it's an empty string +1, so we return a 1. Here, we take the max of 1 and 1. Well, that's just going to be 1, so we return 1. Okay, so this one got a 1 back, we add 1 to it, then we return 2. This one got a 2, we add 1 to it, we return 3. And we're back to our initial call, and our answer is 3, which is exactly what we knew we would get. It's time to write some code. I'm using Python and Jupyter Notebooks, and I've imported our little picture so that we can just use that as a guide. Okay, so let's turn this into words. Let's write some pseudocode. So what does our function do? Our function accepts 2 strings, right? Let's call them string 1 and string 2. Okay, and then what do we do? Let's establish our base case. If either string is empty, return 0. If they're both not empty, then we can look at their last characters. If last characters match, then we can call the function again, passing in the same strings with the last character dropped, right? And then once we get a result from that, we add 1 and return the result. If they don't match, then we have to call the function twice. We'll call the function with string 1 and string 2 with last character dropped. Then we can do the same thing. We can call the function with string 1 with the last character dropped and string 2. Okay, so we'll call those functions, return the bigger of the two. Okay, so that's my pseudocode, kind of rushed, but it's all right. And so now let's turn this into an actual function. So let's call this longest common substring. It takes in string 1 and string 2. Let's establish our base case. If length of string 1 is 0 or length of string 2 is 0, we return 0. Then we look at the last characters. If string 1 at -1 is the same thing as string 2 at -1, we can call LCS again with string 1 with everything but the last character and string 2 with everything but the last character, and add 1, and that's what we want to return. Otherwise, we're going to have to call this twice, call it left, because I'm going to leave the left or the first string intact. We'll drop the last character for string 2. And then for the right, we'll drop the character in string 1, but leave string 2 intact. And then we'll return the max of left and right. There, that's what our diagram and our pseudocode said to do. Let's see if it worked. Let's give ourselves a couple of practice strings. We know that this should return 3, LCS with A and B, and I got 3. Excellent. Let's take the sample from our favorite website. This should give us 4 back. Let's see if it does. And it does. Okay, so we have our recursive solution all written out. Next is our dynamic solution. Let's talk about a weakness in our recursive algorithm. So let's say that our 2 strings are ABC and FGH. So we know right away we're not going to find a common subsequence, but we have to go through what our algorithm would do to figure that out. So C and H don't match. So it's going to split and call the function with ABC and FG. And it's also going to call the function with AB and FGH. From there, C and G do not match. So that means we have to call the function with ABC and F. And we're also going to call it with AB and FG. Over here, B and H do not match. So we're going to have to try calling the algorithm with AB and FG, and also with A and FGH. Here we can see AB and FG, we're going to end up with the same branching problems until we finally get down to our base case and then can start bubbling up. That's a lot of repeated work. So that's the weakness with recursion and why we can take a long time to finish our algorithm. The beauty of dynamic programming is that we don't want to ever have to repeat the work. We want to have a way to store our solutions so that if we ever find out that we have to do the same thing over again, we can just look up the answer. With dynamic programming, we do not want to repeat ourselves. It could be we're storing things in a dictionary, it could be we're storing things in an array. In this case, we're going to use a 2D array or like a matrix. Okay, so let's go back to our example where we had A, B, C, D. And we're trying to find the common subsequences it shares with B, A, C, D. With recursion, we started with our complete strings, and then we broke down the problem into simpler problems until we finally arrived at a base case where the string is empty. With this, we're going to actually start with the empty strings and then work our way up, building in our string until we arrive at our initial strings that we've been given. So let's add in those empty strings here. Okay, and then as promised, we're going to make our matrix. This matrix is going to track longest common subsequences that we can make as we're building our strings from empty strings all the way up to our given strings here. So for example, this cell right here is going to be taking the 2 strings, nothing and nothing. Okay, so if you have nothing and nothing, you cannot build any subsequences. Right away, this one is 0, right? That's our base case. This one is comparing nothing to A, so that's also 0. In fact, this whole top row and this whole left column, these are going to be 0. Because nothing compared to B, we have no common subsequences. Nothing compared to BA, still nothing. Nothing compared to BAC, still nothing. Nothing compared to BACD, still nothing. So those are our base cases written in our matrix right away. Here's the fun part. We're going to fill in the rest of this matrix. Our two substrings that we're looking at here are A and B. When we did this with recursion, then we had our algorithm say, okay, they don't match. So let's split this up, and we're going to do an empty string and B, and we're going to do A to an empty string. Where do we have these answers? Well, we have the empty string to B right here. That's what's happening here. This is an empty string and B, and we know that that answer is 0. An empty string to A is right here, right? That's what's happening in this cell, empty string to A, and that answer is 0. So we can just look left and we can look up, and we have our two answers. And what we're interested in is the bigger answer. In this case, they're both 0. So we'll just take one of those zeros and put it there. Here, what we're looking at is AB and B. When we did this with recursion, then what we noticed was that these B's are a safe addition, right? So we can just say, well, this is the same thing as saying A to an empty string plus 1. So again, where is that A to empty string? That's being stored in this cell right here. So that's the up left, right? So when you move left in this matrix, you're removing a letter from our top string here. And when you're moving up in the matrix, you're removing a letter from this string on the side here. So we want to remove that B from both of them. So we have to move both left and up. We look in that top left cell, we see that that's a 0, and we add 1 to it. So here we know that if our strings were just A, B, and B, we would have a common subsequence of 1. Okay, so now we move on. Now we have A, B, C compared to B. Well, B and C do not match. So we look left, we look up, we take the larger number. B and D also do not match. So we look left, we look up, we take the larger number. In this cell, we're comparing BA to A. A and A match. So we want to drop that A from both of them, meaning that we're going to go and look at our top left cell right here, and we're going to add 1 to it. So 0 plus 1 is 1. So we have a common subsequence of length 1 between B, A, and A, which is clearly true. A and B do not match, so we look left, we look up, we take the larger value, that's 1. A and C do not match, left and up, we take the larger value. A and D do not match, we look left and up, we take the larger value. C and A do not match, so we look left, we look up, we take the larger value. Here, C and B do not match, so left and up take the larger value. C and C here do match. We have BAC compared to ABC. So we go to the top left, we see that 1, we add 1 to it, this cell becomes a 2. C and D do not match. We look left, we look up, we take the larger value, which is that 2. D and A do not match, so we do left and up, we compare them, and we take the larger value. D and B do not match. We look left, we look up, we take the larger. D and C do not match. Left and up, we take the larger value. D and D do match, so we look at the top left, that's a 2, we add 1 to it, and we have 3. This is the value that we end up returning, this bottom right value, because that is the only cell that is comparing what we have been asked to compare, which is the strings A, B, C, D, and B, A, C, D. Let's type up this dynamic solution. I'm back in my Jupyter notebook. I pasted in this matrix that we made to use as a guide, and let's write some pseudocode. So we know that we want to build a matrix, and the dimensions of this matrix matter. We want to have the width correspond to one of the strings and the height correspond to one of the strings, and we have to add 1 to make room for our base case of the empty string. The width is length of string 1 plus 1. It could be string 2, but we'll go with string 1. The length of our 2D array is length of string 2 plus 1. And we can fill it with zeros. We'll have our base cases taken care of already. Then we'll want to go through the inner part of the matrix. And so we started here at position 1, 1, and we compared the characters from the strings that were in the first positions. It's a little bit tricky. We just know that the positions in the matrix will correspond to characters in the strings. Okay, so we'll iterate through the matrix starting at position 1, 1. We'll call that the row, and this is the column. The row minus 1 equals position in string 2, because string 2 is deciding the rows according to how we've written it. The column minus 1 is the position in string 1. We're going to compare the characters. If they match, fill in the cell with the value in upper left cell +1. If they don't match, fill in the cell with the larger of the values from the cells above and to the left. So let's write up this function. I'm going to call it LCSDY. We're going to pass in string 1 and string 2. First thing that we want to do is build that matrix. It's going to be filled with arrays of 0. So we can just use Python list comprehension for this. Let's stick with string 1 being our columns. Now we need to know how many of those rows we need. So that's going to be in the range of length of string 2 + 1. And we're adding 1 so that we have room for our base case. Let's return the matrix and take a look at it. Make sure that we're doing this okay so far. A and B are my ABCD and BACD. That gives me a 5 by 5 matrix. That's looking good so far. So let's keep going. So now we're going to iterate through starting at position 1, 1. Let's go through the rows. So for row in range, and we're going to start at 1, right? We can leave the first row all alone, but we need to start at 1, and we're going to go all the way through the length of the matrix. And then we're going to look at the columns. So again, we're going to start at 1, and we want to go side by side. So we just, the width of the first row in the matrix will do. So if string 1 at column minus 1 equals string 2 at row minus 1, right? So that would mean the last characters match. Then we want to take the upper left and +1. So wherever we are now, matrix at row column is going to be equal to matrix at row minus 1, column minus 1, +1. If they don't match, then we need to look up and the left, and then we're going to say matrix at row column is equal to the max of up and left. Okay, and then we don't want to return the matrix, we want to return the last row, last column. So that's just matrix -1, -1. And let's see if that gives us 3. And it does. Let's try it with the other example that we had. Okay, this should return 4 to us. And it does. Okay, so here's where it can get really fun. So let's make up some crazy test cases. So let's do C equals, there's a whole lot in there. Okay, and D, let's see how long it takes our recursive solution to come up with an answer. So we'll put that in a timer. Okay, and let's run that. And in the meantime, I'll set up my dynamic solution. Okay, so up here, our recursive solution took 2.79 seconds. The longest common subsequence is 21 long. So that's, again, 2.79 seconds. Looking down to our dynamic solution, it took 392 microseconds. Microseconds. So we went from seconds to microseconds with our dynamic solution. That is pretty cool. I mean, if that doesn't just thrill you, I don't know what will. Now, if you want to get technical about it, and I know you do, let's talk about it in terms of big O. When we're talking about big O time complexity, we're talking about the worst case scenario for our algorithm's runtime. So with our dynamic solution, this is actually quite a bit easier because all we're trying to do is fill in the matrix, and the dimensions of the matrix
is determined by the lengths of the strings. So it's going to be an m by n matrix, m being the length of string 1, n being the length of string 2. I guess technically m plus 1 by n plus 1, but no one cares. Okay, so we could say that it's the big O of m by n, kind of similar to O of n squared if we knew that the strings were the same length, but this is m by n because we don't know that they're the same length. Contrast that with our recursive solution. Our worst case scenario is when there are no matches, so that with every call of the function, we have to try two different things. We have to try removing a letter from both strings. So in this case, A, B, C, D, E, F, right? We have to branch and we have to try A, B, C, and D, E, and we have to try A, B with D, E, F, right? And then we're gonna have to branch again and again. Every level in this recursive tree, we're doubling the number of calls. And then how deep is this tree going to go? There's going to be keeping the ABC intact as we remove strings from this DE. We are also going to have to try removing the letters from the first string. So we would have to go from to AB and D, and then to A and D. The depth of this recursive tree is going to be m plus n, right? Because we have to first whittle away the first string, and then we have to whittle away the second string. We're going to have how many calls, right? It's going to be 2 to the power of m plus n. That's a lot worse than an m by n big O.